Hello everyone, my name is Shravan Muthukrishnan. I'm a PhD student with Professor Jay Sanjan and Saindan Ramakrishnan. I'm doing my research at Swinburne University of Technology, Houghton right now. I have submitted my thesis, so I'm waiting for examiners' comments. And meanwhile, I was fortunate enough to get a postdoc opportunity with Professor Victor Mescherin from TU Dresden. So if all visa processes are coming on time, I'll be in Dresden, Germany from May and continue my research on concrete as a postdoc. So today I'll be presenting on set-on-demand geopolymers for concrete 3D printing. But before I jump into the results, I thought of giving a very short introduction on what concrete 3D printing is. So concrete 3D printing, as many of you know, is a digital and foamer-free construction technique where the fresh concrete is placed layer by layer until the design structure is built. In the last few decades, this technique has gained enormous attention amongst researchers and industries because of the various advantages it possesses. And some of those advantages are concrete 3D printing being faster, cheaper, and providing like ultimate design flexibility, which traditional construction kind of lacks. But unfortunately, the cement which we used, it's the cement content of the printable mixes. Most of the printable mixes are very high compared to the traditional concrete, because of which the sustainability index of the printable concrete is low, and it reduces the whole sustainability of the 3D printing processes. This can be solved in two major ways. One is by using large aggregates, like how we do in traditional concrete, is that the large aggregates consumes high volume in the concrete mix such that the cement content reduces automatically, or replace the cement with eco-friendly alternative like geopolymers. And in my study, I have chosen the later strategy to increase the sustainability of printable indexes because we have plenty of fly ash and SCMs available in Australia. So we developed fly ash and geopolymer based printable mixes, and we used them to print structures. And when we printed those structures, we found out that there were a lot of limitations with geopolymers. And one of the major ones are chemical admixtures, which have been like actively used to attain the rheology in cementitious mixes, cannot be used with geopolymers. For instance, admixtures like superplasticizer, set retarders, set accelerators, we cannot use them in geopolymers because these admixtures requires OPC for activation, and geopolymer doesn't have OPC in it. So if you want to increase buildability of a geopolymer printable mix, the only best option you have is adding thixotropic additives like nanoclay. But if you add nanoclay during the initial mixing stage, it does increase the static yield strength, which will help increase the buildability of the concrete, but that increment in the static yield strength also reduces the pumpability of the concrete. So any level of buildability enhancement you can achieve using adding nanoclay in the initial mixing stage is constrained by pumpability limitation. So the reference which I have shown below, we have done an in-depth analysis to find out that optimum dosage at which you can have a reasonable buildability, but without significantly losing pumpability of the mix. And we found out that you can have a building rate of 0.03 meter per minute using nanoclay, but you will only have an open time of 45 minutes. So if you have a mix with 45 minutes open time, that's a huge setback for that mix's large-scale implementation. Because if you have a print site somewhere far away from the batching plant, after mixing, you have to transport the concrete and print it within 45 minutes, which is very challenging. So we developed a new geopolymer mix by just varying the activator type and dosage, and came up with a new mix with an open time of 2 hours. And we tried to print using that mix. So during the pumping stage, the mix was able to pump smoothly for 2 hours, but once it leaves the nozzle, the buildability of the mix was so bad that we could only print up to 3 layers. Anything above that released in complete failure. So to increase the buildability, what we did was we provided some kind of thermal interventions of the printhead, like microwave heating in this case, and we increased the buildability of the mix. So when you have this thermal intervention of the printhead, the enhancement in the buildability due to this effect doesn't influence the pumping stage. So you will have a mix of 2-hour open time, which is pumped to the printhead, and the microwave heating is applied there to increase the setting rate of the concrete, thus the buildability of the concrete. So from the preliminary analysis or the study, the feasibility study, we found out that we just require 10 seconds of heating at the printhead to get a buildability enhancement of 7 times what we achieved using nanoclay, but also maintain a really high open time of 2 hours compared to 45 minutes with nanoclay. So to validate this concept, we developed a suitable printhead and we tried printing a second. So before printing, we got a major backlash from safety officer saying that we had to go through some kind of safety clearances process because we are using microwave radiation for heating. And it has been 2 years from the day we submitted the application and we haven't received the safety clearance yet. So we imagine what would have been the case in large-scale construction, because the printer used is definitely bigger than what we use here, and the filament width is also it's gonna be bigger than what we're gonna print in the lab scale. Therefore, the printhead also will be larger than what we developed here. So for that larger printhead, getting a safety clearance will be a major limitation for this approach to be implemented. And therefore, even though the results are so promising, using microwave radiation to attain that could be a limitation because of the work safety issues. So we developed a new method where we prepared a rapid setting geopolymer concrete. And what I mean by rapid setting geopolymer concrete is that once the concrete is prepared, it will have an initial setting time of 5 to 10 minutes. So once this concrete is prepared, we divide the mix into 2 parts, the dry ingredients and the wet ingredients. And we plan to pump the dry ingredients to the printhead, and the wet ingredients will be used to mix with the dry ingredients of the printhead, and the resultant concrete will be extruded as printed layers. So for this particular technique to be successful, we have to make sure the mix has 2 important properties. One, once the mixing is done, the resultant concrete should have enough initial static yield strength such that the printed layers have some kind of shape retention. If the initial static yield strength is too low, then the extruded concrete will just deform. It won't maintain its own shape. And secondly, the static yield strength development rate should also be high, such that once this the first printed layers is stacked by subsequent layers, the load from the subsequent layers doesn't deform the first layer. So for this particular approach to be successful, these 2 properties has to be there. And we found out that the initial static yield strength and the static yield strength development rate is quite sensitive with the silicate modulus of the activated solution. Silicate modulus is nothing but the ratio of SiO2 and Na2O from the activated solution. So when you have a really low silicate modulus, somewhere around 0.5, you will get a high initial static yield strength, which will allow your layer to have that beautiful shape while extruding, but the setting rate or the static yield strength development rate is too slow. So you can't have good buildability. You have to print really slow. But when you gradually increase the silicate modulus, although the setting rate or the static yield strength development rate increases, your initial static yield stress reduces. So you can't have that beautiful shape of the extruded layer. But at certain points, somewhere around 2.15, we get the best of both the properties. And this particular paper, which I have referred in this particular slide, gives you a comprehensive analysis of how we achieved that silicate modulus and how we came up with a suitable set-on-demand geopolymer mix design. So we found out that with all this optimization, the buildability you can achieve is around 4.5 meter per minute, which is 150 times higher than the nanoclay mixes. And the open time is infinite because your dry ingredients is what is pumped at the concrete at the printhead, and your activated solution is what it is pumped at the printhead. So these 2 components, if they are not mixed together, they can just stay inside the pipeline for ages. They won't set at all. But there was another major thing which I should mention here is that usually the geopolymer concrete, when you prepare, in lab scale or in large scale, you need at least 5 to 6 minutes of mixing time. But if you have 5 to 6 minutes of mixing time at the printhead, you will require a really large printhead for printing. And just imagine having a gigantic printhead next to the nozzle, and the hindrances it can provide when you try to print intricate structures, right? So we try to reduce the mixing time by increasing the mixing speed, and we found out that when the speed is increased up to 750 rpm, the mixing efficiency increases significantly, such that your mixing time can be reduced from 5 minutes to 45 seconds. We have also achieved a mixing time of 10 seconds by increasing the mixing speed to 1000 rpm, but that was not reported in the study. We did that study sometimes after we published this paper. So I guess if I remember it right, the best operating parameters which we have achieved right now is 1100 rpm with a mixing time of 10 seconds. And we got the same mixing efficiency like we can achieve with 5 minutes of mixing in a normal concrete mixer. Now, even though the previous results were quite promising, it's really hard at the moment. It's hard to implement in large scale because we don't have a suitable pump to transfer a blend of dry ingredients from point A to a moving printhead. Right now in lab-based study, we use a manual approach. We pre-blend the dry mix and use our hands to put it on the hopper of the printhead, and from the hopper it goes to the printhead, mixes with the activated solution, and extrudes the concrete. But that particular approach cannot be used in large scale, and until we get a suitable pump, implementation of that particular approach can be challenging. So we came up with a new strategy, which is nothing but an extension of the previous strategy, where we mix the dry ingredients with water and pump it as slurry to the printhead and activate with the activated solution. As you could see from these two videos, this approach worked perfectly well. We got initial static yield strength to maintain the shape of the printed layer, and also the static yield strength development rate required for good buildability. As you could see in the right hand side video, printing overhang this kind of overhang I don't think can be printed with nano clay. This is something which we are really proud about, what we have achieved with geopolymer, cetronimon geopolymer per se. But comparative to the previous approach, this approach has a small limitation, can be a big limitation as well, is that the water from the slurry, when it is mixed with the activated solution, it dilutes the activated solution and it reduces the compressive strength or the hardened properties of the concrete. And in the future studies, we have come up with new strategies, new mix designs, which takes care of the dilution. And we have a mix right now. We can proudly say that we have a mix which has all the fresh properties required for cetronimon geopolymer concrete, and that mix have also exhibited sufficient hardened properties and durability, which I have mentioned in my thesis. So once it is available online, I'll share it with you all guys. So this brings to my last slide. So the main conclusions which we could make from this presentation is that the commercial available mixers such as retarders and accelerators, which work really well with cementitious mixes, doesn't work with geopolymer at all. So to get this contradictory rheological properties, we need to come up with a new technology. Buildability enhancing additives doesn't work. If you add nanoclay during the initial mixing stage, it does increase the buildability of the mix, but it also reduces the pumpability of the mix. So any increment in buildability is always in expense of pumpability reduction of the mix. Geopolymer precursors, unlike cement, when added with water, it doesn't react. Cement, when you add with water, the time starts ticking because hydration process starts to take place. But geopolymer precursor, it doesn't happen like that. You need to activate using activated solution. So we can have a strategy called inline activation, where the precursors can mix with water, and that study will have a really long open time because nothing happens for that mix, chemically at least. And once that is sent to the printhead, you can activate using the activated solution, and get the buildability which you want. So you can have both open time, both high open time, and good buildability without using the chemical admixtures like set retarders and set accelerators. The liquid-liquid inline activation method is currently the best method because we have pumps to pump both the liquid ingredients at a precise dosage. Dry liquid could be better, but we don't have pump to do it. But when you have two liquids, the total water content of the mix increases significantly, which hampers or can be detrimental to compressive strength and durability. But we can always change the mix design geopolymer because it is highly customizable and get the hardened properties and durability required. Yeah. Last but not the least, I'm very active in social media. You can always find me in LinkedIn, Twitter, Google Scholar, and ResearchGate. So you can, if you can't get my email ID from this presentation, you can always search my name, Shravan Muthukrishnan, in ResearchGate or Google Scholar, and or LinkedIn, or you can just reach me there. Thank you very much for your patience, and I appreciate all the question and answers you have, and I'll be trying my best to answer them. Thank you so much.